Hi, and welcome to this presentation of the choice of normalization influences shrinkage in regularized regression. My name is Johan, and this is joint work together with Jonas Wallin. In this paper, we studied the elastic net, which is a type of regularized regression problem where you take the ordinary least squares objective and add a penalty term that's a combination of a lasso penalty and a ridge penalty, which is a L1 penalty and a squared L2 norm penalty, respectively. These are controlled by lambda1 and lambda2 parameters. If you turn these problems into constraint problems, then ridge regression yields a disk as a constraint region, and lasso yields a diamond shape, and elastic net is a combination of the two. As you can see in these plots, elastic net and lasso can yield sparse solution, whereas ridge does not generally. The problem with the elastic net is that you typically don't know how to pick lambda1 and lambda2 in advance, and instead you have to use hyperparameter optimization, for instance cross-validation, to pick these. And a common parameterization when doing this is to set lambda1 equals to alpha times lambda and lambda2 equals 1 minus alpha times lambda, with alpha set between 1 and 0. And if you then set alpha to 0, you get only a ridge penalty, and if you set it to 1, you get only a lasso penalty. And then for each alpha, then you solve the elastic net over a sequence of different lambdas. And this is called the elastic net path. And you can see an example of this on the right here. Notice that we start on the left-hand side of this plot and that the x-axis is reversed so that we have increasing values of lambda. And as you see, when we increase lambda, one by one the features start to become selected, start to enter the model, and their coefficients become non-zero. The problem with lasso and ridge penalties are that they are norms, and because of this, feature scales matter. So the scales of your features in your problem, they are going to matter. And for a simple example of that, let's assume that we have sampled our design matrix X from a multivariate normal distribution with two independent features with zero means and with standard deviation 2 and 1 and with the true coefficients set to 1/2 and 1. And then we generate our response vector y from a linear combination of x and beta and add some noise on top of that. In this case, the two features have equivalent effect on the response, because if you move a standard deviation on either of them, you get an equivalent effect on y. And this is represented in the OLS model, so the ordinary least squares model. In the unscaled coefficients, you get 0.5 and 1, but in the standardized coefficients, so when you've divided by standard deviation, you get 1 and 1. And the interpretation here is that they have the same kind of importance for the response. But that's not the case for the lasso. So you can see that both for the unscaled coefficients and for the standardized coefficients, the lasso, it has different coefficients for the two features. And this is also the case for ridge. So in other words, if you have a large scale, then it means that you can have less penalization because the size of beta j can be smaller for an equivalent effect on the response. This is of course a problem because it doesn't correspond to what our interpretation should be of this problem. And the way to fix this is this kind of scale sensitivity is by normalizing the features. And we're going to let x tilde be our normalized feature matrix, where we have subtracted a centering factor c and divided by a scaling factor s. So these two are vectors of the same number of elements as there are features in your problem. Then after fitting, you transform the coefficients back to the original scale via this transformation, where you divide the unscaled coefficients by the scaling factor. And if you were doing standardization, for instance, then Sj would be the standard deviation of each of these features. There are, however, many ways to do this kind of normalization, not just standardization. And if you are into statistics like I am, then standardization is probably what you are most used to doing. But in other fields, it's also common to do, for instance, L1 normalization, where you replace the L2 norm from standardization with the L1 norm instead. Or you can also do maximum absolute value normalization, for instance, or min-max normalization. Both of these, they retain sparsity if you have binary features, so they are typically used and are popular when you have large data sets with binary features and where they are sparse. But which of these you pick also have an impact on the final model that you get from fitting to your real data sets. And to see how this works, we have two data sets here, triasigns and W1A, and we have tried to fit lasso paths to them using two different normalization schemes. So in the first case, or in the top row, we have standardization, and in the second row, we have maximum absolute normalization, where you have no centering term and only scale with the maximum value of each feature, maximum absolute value of each feature. In these plots, we've colored the first 5 coefficients to have entered the model under each of these regimes, under each of these types of normalization, which means that if the colors are different, then they correspond to, then the two normalization schemes yield at least partially different models. What we can see here is that both the coefficient paths and which features are selected differ starkly between the two normalization schemes. And here's another example where we have taken the two same data sets but added another one, Boston-Hausen data set. And instead of just fitting lasso paths here, we have done 5-fold cross-validation, repeated 5 times. And we've picked and are showing the 5 coefficients with the largest magnitudes in the standardization scheme, but are also showing the corresponding coefficient from the maximum absolute value scheme. And as you can see, for instance, from the triasigns example here, the two models that you get from cross-validation, if you try to pick lambda, are very different. In the triasigns case, the 5 largest coefficients that it picks, they aren't even selected in the maximum absolute value scheme. So, normalization clearly matters. But when you look into the amount of research that has been done on this field, there is none at all. Everyone agrees that you need to normalize, but how to do so is usually motivated by just being standard. And what's more is that this definition of what standard is, it depends on which field you are in. So if you are in statistics, you are doing standardization most of the time. But if you are in machine learning, you will probably be more used to doing maximum absolute normalization. And if you're into signal processing, it might be the case that you are used to doing L1 normalization, for instance. What we show in our paper and what we study is how normalization influences shrinkage. We focus on the elastic net, which we've already introduced, and also on binary features. And we will show in our paper that there is a bias variance trade-off that depends on normalization. So bias and variance in terms of the coefficient estimates, which means that you get an effect of normalization on how much shrinkage you get on your coefficients. And for the elastic net, we also show that you need to scale the penalty weights, not the features themselves, to be able to get rid of this bias. And in addition, when you mix binary and normal features, which is often the case, normalization implicitly is going to weigh how much shrinkage you do on normal features versus binary features. But before we get into some of the more experimental side of our papers, we're going to tackle a bit of theory. Because this is a hard problem to analyze, and because there is no explicit solution to the elastic net problem in general, we have assumed in our work that the features are orthogonal to one another, which means that the inner product of the design matrix, the normalized design matrix, is diagonal. And in that case, you can actually solve for each of the coefficients individually, which is an expression involving the soft thresholding operator and a scaling parameter. So one term in the denominator that comes from rich regression, and another term that is related to the lasso part. And if we now assume that we have a binary feature, x, j, where each value takes either a value of 0 or 1, and we let q be the class balance of this feature, the mean of this feature, so that if you have 1/2, it's perfectly balanced, and there are half of the elements are 0 and half of them are 1. Then in the noiseless case, you can see that the estimator for each of the coefficients is the following expression, where we highlighted the impact of class balance, the q's here in each of the terms. This means that for ridge, lasso, and the elastic net, the class balance has a direct effect on how much shrinkage you do. And also in the case of the lasso, whether or not the feature gets selected or not. And it suggests that if you pick Sj equals to Q minus Q squared, which is the variance of each binary feature, and for the lasso, and for ridge, pick the square root of this, which is the standard deviation, then you can remove this effect entirely from the estimator. So you can basically remove this bias that comes from class balance, but only for the lasso and ridge on their own. And in fact, this also suggests that there is no simple way to get rid of this effect for the elastic net. And altogether, this suggests a kind of parameterization for scaling here that is a power of the variance of the binary feature. We're going to use this, and we've used this in our paper, and going to use this throughout this presentation, where we take the variance of the feature and raise it to the power of delta. If we move on to consider a case where we now add noise, we keep x, our features, fixed, and add noise, then we can actually compute the probability of selection for each of the features. So the probability that the corresponding coefficient for each feature is non-zero. We've computed this in this plot for 4 different levels of noise, sigma e. And on the x-axis, we have the class balance here. So as you move to the right, the given feature, the binary feature, becomes less and less balanced. This is plotted for 5 different levels of our delta parameter, which controls normalization. In the case of delta equals to 0, so the red line, you have no scaling at all of the binary features, whereas if you have 1/2, then you have standardization, and 1 corresponds to scaling with variance. You can see that the probability of selecting each of these features, it decreases when the feature becomes more and more imbalanced. And you can see that this is more pronounced when you have a lower level of delta. So if you have no scaling whatsoever on your features, then it's quickly going to drop to 0, the probability that this binary feature is going to be selected. This is related to the bias variance trade-off that we mentioned earlier as well. So bias in terms of estimating your coefficient and how close it is to the true value of that coefficient. So it's always the case when you have regularization, of course, that you are introducing bias, but it's also going to depend directly on the level of normalization that you have. And we have also shown here variance here and the mean squared error. And as in the last slide, we're showing this for the 4 level of noise that we have previously. You can see that the level of bias here, it depends directly on the normalization scheme that you do, but it also connects closely to the noise level that you have. So if you have a low noise level, then this bias is going to be more pronounced, but for higher noise levels, it's going to be less pronounced for the different levels of normalization. Now we turn to some experiments. So in this case, we have similar data from 500 observations and 1,000 features. We're showing the lasso estimates for the first 30 coefficients in this example, where the 21st features correspond to features that have true signals set to 1. And the class balance here, it's geometrically decreasing from 0.5, so a completely balanced case, to 0.99, so a very unbalanced case. And you can see this, that the different rows here correspond to different normalization schemes. So roughly speaking, the top one is the unscaled case, so equal to the maximum absolute value normalization and min-max normalization types. The middle one is standardization, and the lowest one, delta equals to 1, is equal to scaling with variance. You can see here that the estimates for the different features, even though they have the same true coefficients, they drop to 0 as you start approaching, or as the class balance increases. And this also relates to the columns of this plot, which correspond to different levels of correlation. So in the leftmost plot, we have no correlation between the different features, and in the rightmost plot, we have a correlation that's not exactly equal to 0.9, but it's a sort of pseudo measure of autocorrelation between the different features. Here's a simple example where we have involved just 2 features. where one is a binary feature as before, but the other one is a normal feature. The normal feature we always standardize in each of these examples. We have fit both lasso and ridge in these cases, but have tried different levels of our delta parameters, our normalization parameter. And you can see that the cases where the two coefficients that we in this example want to have the same effect of, where they are only equal in the cases where delta is equal to 0.5 in the ridge case and where it's equal to 1 in the lasso case. In all other cases, class balance has a direct effect on the coefficient estimates. So we've shown that the type of normalization matters for which features are selected, so it's also natural to consider whether this might matter for the loss of these different models. And the answer is that it does. And it suggests that you can actually do hyperparameter optimization for your problems. And we've shown a simple example of doing this for lasso and ridge here, and for 3 different data sets, RE 2006, EUnite 2001, and TriAssigns, where we've shown normalized mean squared error in these contour plots. And what you can see here is that the level of delta matters for many of these cases, which suggests that you should actually, or you may consider, doing hyperparameter optimization also for delta and not just, for instance, for lambda and alpha in your elastic net problems. So in summary, we've shown that class balance plays a crucial role when it comes to using regularized regression, like the elastic net, on binary data. This is the first paper to investigate this interplay between normalization and regularization, which was a surprising finding to us and which we hope can lead to more people and scientists researching this in the future. We introduced a new scaling approach, this parameterization using delta, that allows us to control this bias and variance trade-off that we showed. There are many more details in our paper. For instance, considering the case of mixed data closely, where we have binary features and normal features, and how the implicit weighting problem that we mentioned earlier on this talk comes into play. We also discuss interactions between features and how you should scale those and center those to be able to attain as unbiased effect as possible. We also discuss the weighted elastic net, which is the solution to the problem of having the elastic net depend on the class balance case for any kind of feature normalization scheme. There are also many more experiments on real and simulated data in this paper, so please check it out. Thank you.